Welcome to the afternoon session of EuChemS workshop on rare earth elements. Today in the morning we had a section at the European Parliament that was an exciting section dealing with several different topics, and I still want to thank for this Annalisa Corrado, that was the host, and Peter Roski, that was the chair of the scientific part of this meeting. That was really very much interesting. That was because it was related to the general problem, geopolitical problem, and also focused on the problem of recycling, processing, and extraction of these elements that are so critical for our future. So we start this afternoon session talking a little bit more in deep what are the application of rare earth elements from several points of view, starting with the first speaker. Then is Andres Mejering from Utrecht University. He will talk about optical properties of rare earth elements, materials, and their applications. Few words on André Mejering. Then Hern is PhD at Utrecht University, followed by a postdoc at the University of Wisconsin. Since 1996, he has been chair of solid-state chemistry at Utrecht Dubai Institute. His work addresses light conversion with LEDs, display solar cell, and fiber amplifier, as well as quantum confinement and exciton dynamics in quantum dot and open nanocrystals. And he received numerous awards and has been elected also at the Royal Netherlands Academy of Science. Please, the first speaker, the floor is yours.
If you want, you can, yeah.
Yeah, thank you for the kind introduction. It's a real pleasure to speak here. And as you indicated, this morning was wonderful. A lot on rare earths, mining, criticality, recycling. Now we go a bit more into the science. So I will discuss the optical properties of rare earths and their applications. Yes. Yes.
Shift a little bit this on this side because we cover.
Okay.
Yeah.
Yes.
Is better?
So what I will discover, I will give a short introduction to rare earths. Rare earths have already been introduced, but maybe I can add a little bit. And then I will cover spectral conversion with rare earths, the optical properties. I will give an overview of applications, and I cannot explain them all, but I will discuss fluorescent tubes, also a topic of this morning, white light LEDs, displays, lasers, fiber amplifiers, solar cells, and not unimportant, money, and I will end with conclusions. And then if times, I may have a chemistry as well. So the lanthanoides, yeah, they're at the periodic tables mentioned, they're hidden, people don't know them. And actually it's also in the name of the lanthanoides. The name lanthanide comes from the Greek word lanthanain, which means to lie hidden. And they're indeed hidden at the bottom of the periodic table. Now, if you look at the lanthanoids, it's a group of elements where an inner 4f shell is filled. And in high school, we learn how the orbitals are filled. First the 1s, the 2s, according to the Aufbau principle, then the 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. And only after the 5s, 5p, and 6s orbitals are filled with electrons, only then this inner 4f shell is filled. And this partly filled 4f shell That gives the lanthanides their unique optical properties and also magnetic properties. So, yeah, so this has been covered. They're not rare. They're quite common. Very famous picture. The most abundant is cerium, very similar to copper and zinc. The rares of the rare earth is thulium, even more abundant than silver. So they're not rare, but they are unique. And as I mentioned, these unique properties comes from this partly filled inner 4F shell. If you look as an example to terbium 3+, it has the electron configuration xenon, 4Fn, 5s2, 5p6, and N, the number of electrons in the 4F shell for terbium is 8. Now, if you have 7 f orbitals, in every f orbital you can put 2 electrons. You have basically 14 orbitals that can be occupied by electrons. And when you put 8 electrons in, the number of ways you can arrange those 8 electrons over the 14 f orbitals is 14 over 8. The same for you have 14 cups, 8 marbles. The number of ways you can arrange those 8 marbles over the 14 cups is 14 over 8. 3,003 different ways. And now the interesting thing for optical spectroscopy is that all those 3,003 different ways of arranging the electrons over the 14 f orbitals can have a different energy. So you have very rich energy level structure. The ground state is the most favorable way to put electrons in, and that's determined by Hund's rule. And Hund's rule says as much as possible, we put the electron spins parallel. So the ground state of terbium looks like this. We have the 7 f orbitals, and the first 7 electrons go in with spin parallel. Then the 8th electron, of course, cannot also have a spin parallel. Then we have 2 electrons in the same orbital. That's not allowed. Pauli's principle forbids that. So the 8th electron has to go there. So this is one electron configuration that belongs to the ground state, lowest energy state for terbium 3+. But then there's still 3,002 other ways of putting those electrons in. Now this electron configuration also helps you understand why they're so good for magnets. And I think the next talk will address that. But where you can see that all those electron spins parallel gives a very high magnetic moment. And that's crucial for applications in wind turbines, where especially neodymium iron boride magnetic material has a much higher magnetization than any other 3D transition metal material. And that gives wind turbines a much higher efficiency. But we will talk about the optical properties. Here we see on the right the energy level scheme or part of the energy level scheme of terbium. So the ground state, one electron configuration is given there with the 7 electrons parallel, the 8 paired. Those energy levels have names. You don't have to understand the names to understand the spectroscopy of lanthanides. The ground state is called 7f6. It's a term symbol. It has information on the alignment of the spins and the orbital occupation. For now, we can just consider the name. So that's the ground state, 7f6. But then there's 3,002 other configurations of those 8 4F electrons that gives rise to many energy levels. So here's a function of energy in wave numbers. The energy levels, part of them are given for terbium. So we see 7f6 ground state, then there's 7f5 to 7f0. Then there's nothing for a while, then around 20,000 wave numbers corresponding to photon energies of 500 nanometers. There's the 5d4 level, and then a bit higher again in the UV, there's the 5d3 level, and then it continues many, many levels, all the way to about 170,000 wave numbers. Many, many energy levels. Now, if you look at the luminescence, the emission spectrum of terbium, it's shown here. And that is quite unique. If you excite in the UV from the ground state, because normally terbium is in the ground state, but we excite with UV photons that are resonant with transition from the ground state to the 5d3 in the UV, the terbium is excited at the 5d3 level. Then it relaxes by giving off some energy and vibrations, heat, to the 5d4 level. And then the gap to the next low level is so large that from the 5d4 level, the terbium returns to the ground state by emitting light. And it does that in a very special way. There we see the emission spectrum. And you see some sharp lines around 490 nanometers. That's due to the transition from 5d4 all the way back to 7f6. Around 550 nanometers, you see some sharp lines due to 5d4, 7f5. Around 590, 5d4, 7f4. And what is special about this is that it's very sharp emission lines. And that is unusual. Normally, if you have ions in the solid state or ions in solution or organic molecules, you get broad emission bands. And the reason is there's a strong coupling with vibrations. So we have combined electronic and vibrational transitions, vibronic bands. You get broad bands, not for the lanthanides. This transition takes place in this inner 4F shell that is shielded from the environment by the 5s and the 5p. So those transitions have very weak coupling with the environment. So you get atomic-like sharp zero phonon lines. And that is really unique for the lanthanides and very profitable for many applications. Another special thing is that it's independent of the matrix. If you have terbium dissolved in water, or you have terbium in an oxide host, or you have terbium in a fluoride host, doesn't matter. This energy level scheme is always the same. The reason is again the same. Those energy levels arise from interactions between those 8 forever electrons in this infrared shell, shielded by the 5s and the 5p, no interaction with the environment, so it doesn't matter whether it's an oxide or in a nitride or a fluoride. Very different from the transition metals. You may know that chromium 3+ in ruby gives a red color. Chromium 3+ in many other compounds, like beryllium aluminum oxide, gives a green color. Depending on the host, the crystal field splitting changes and the optical properties, everything changes. Not for the lanthanides. This energy level scheme is always the same because it arises from this well-shielded inner forever shell. And finally, important for applications, the quantum yield, and the quantum yield is defined as the number of photons emitted divided by the number of photons absorbed, is very high. And again, the same reason. You're in the 5-4 level. Now, 2 things can happen. It can emit light, radiative decay, or it can give the energy to vibrations. Non-radiative decay, then it is transformed into heat. Because of the shielding and the weak interaction with vibrations, lanthanides have the capability of emitting light with almost 100% quantum yield. And for optical applications, that is very important. So this was the energy level scheme of terbium. If you look at all lanthanides, then we see here the energy level of all lanthanides. And you see there's many energy levels in the infrared, in the visible, in the UV. It's called a decay diagram, a rather complex picture if you don't know the field. But the nice thing is it never changes. So if, like me, you've worked for over 30 years in the field, and I see an emission spectrum, I mean, oh, that's erbium, that's terbium. And also it's our toolbox for spectral conversion. If you need to convert one wavelength to another wavelength, I go to my decay diagram and look, oh yeah, this wavelength can be absorbed by this ion and maybe can transfer to the other ion. So this is a very flexible collection of energy levels that you can use for any type of spectral conversion. In all spectral regions that may be relevant for certain applications. Now, what are applications of the optical products for lanthanides? This is not even an exhaustive list, but they're used in fluorescent tubes and compact fluorescent tubes, white light LEDs, displays, liquid crystal displays, plasma display panels, medical imaging. I will not talk about it, but X-ray imaging, traditional X-ray images, CT scanners, computer tomography, but also PET scanners, post-emission tomography. They all use lanthanides, lanthanide doped materials to convert the X-rays into visible light, which is then detected. Afterglow materials, like you see there, to find the emergency exit, or as decorations in stars in children's bedrooms or toys. Lasers, fiber amplifiers, solar cells, a possible future application to make solar cells more efficient, and also money. The ones in red I will cover. So first, fluorescent tubes and compact fluorescent tubes. Works as follows. You have a glass tube. In the glass tube there's a little bit of mercury. You turn on the fluorescent tube, the mercury evaporates, and then current passes through the mercury vapor. The electrons are accelerated from the negative to the positive electrode, collide with the mercury atoms get to an excited state, and return to the ground state by emitting light. But UV radiation, mostly around 254 nanometers. The process is very efficient, about 70% energy efficiency. So if you put in 10 watts of electrical energy, you get 7 watts of UV radiation out. The problem is you cannot see it. So on the inside of the fluorescent tube, there's a coating of phosphors, of luminescent materials that absorb the UV and convert UV radiation into red, green, and blue light. And then, if you combine it in the right ratio, you get white light. And the phosphors that are used in all compact fluorescent tubes and fluorescent tubes are yttrium oxide europium for the red light, lanthanum phosphate with cerium and terbium. Cerium absorbs UV, transfers the energy to terbium, terbium emits green light, and barium magnesium aluminate with europium 2+, absorbing UV and emitting blue light. And if you mix them in the right ratio, 2 scoops of red, 2 scoops of green, 1 scoop of blue, mix it up, then you get a white luminescent material. You can also change the color. If you want warmer white light, you add more of the red. If you want cooler white light, you add more of the blue and the green. So that is a very nice concept to efficiently make white light. But the future of lighting is white light LEDs. And of course, that it was the future was already predicted by the Beatles. Let it be. It's based on invention by those three great Japanese scientists, Akasaki, Amano, and Nakamura, they invented around 1990 the blue LED. Before 1990, we already had red LEDs and green LEDs, and yeah, that's nice. But to make white light, you need blue, green, and red. Now, to convert green photons into blue photons is difficult because you have to go up in energy. You can do it, but never efficiently. But once you have a blue LED, you can very efficiently convert part of the blue to green and red to make white light. And in 1996, at the company Nichia, where Nakamura also invented the blue LED, he combined the blue LED with a yellow phosphor, YAG, cerium, yttrium, aluminum, garnet. That's the host letters, doped with cerium ions, and cerium ions do the work. They absorb the blue light, convert it into yellow light. And now here you see how the LED works. Part of the blue light is absorbed, converted into yellow. Part of the blue light is transmitted, and the blue combined with the yellow is white light. And you can also see it if you look at your mobile phone. In the back, you may see the flashlight. You see a little yellowish dot. That is YAG cerium. Now, to make warmer white light, you can see here that the spectrum lacks red. Red is beyond 600 nanometers. This is really a cool white LED, not very pleasant. To make it more warm white, you add red emitting phosphors like calcium aluminum silicon nitride doped with europium 2+. Again, a lanthanide. And here you see some of the phosphors under UV radiation. Now, there's a lot of research going on in the field of LEDs. And here I just list some of the things that are going on. You can make white light by blue with PC yellow. PC does not mean politically correct, but phosphor converted yellow. That gives you cool white. If you combine it with red LED, you get warmer white, but you can also have a blue LED with a green and a red phosphor. You can have UV LEDs, the same material, indium gallium nitride, that is used for the blue LED. If you have a little bit less indium, more gallium, you can shift that LED to the near UV, and then you can have UV LED with a blue, a green, and a red emitting phosphor. And also a big development is to replace the light emitting diode by a diode laser. Then you can get much brighter light sources. But for that, we also need new phosphors, new materials. But an application there is in the automotive, where you have really beams that are very far ahead, or projectors for projecting presentations. Also lighting for horticulture, human-centric lighting. You can change the spectrum to affect your health, being more awake or more sleepy at night. So those are emerging markets where we need new materials. And the field where I work in, there's many new materials being discovered. Narrow band emitters are also good for energy efficiency. Oxynitrides, nitrides, quantum dots. And I explained that the optical properties of lanthanides are really unique. And this morning it was mentioned that initially the EU said, well, we have to go for replacement of lanthanides with other ions, substitute. And indeed, the efficiency of lanthanide is unparalleled. And for many applications, we cannot replace them. But in some applications, also 3D transition metal phosphors are doing a good job. For example, manganese 4+. LCD screens, displays. Also there, we use LEDs where lanthanides do the job to convert blue light into green and red light. This is the configuration of a liquid crystal display. And I will not explain it here, but the important part is that for liquid crystal displays, you need backlights. And those backlights are again white light LEDs where lanthanides convert the blue light into green and red narrowband emission. Lasers and fiber amplifiers, another big field where we use the unique energy level schemes of lanthanides. For example, neodymium lasers are widely used. Here you see some examples of applications of neodymium-based lasers. They use the energy levels of neodymium, the 4s3/2 to 4i11/2 transition, around 1060 nanometers. Used in laser pointers that you may know, very small scale application, very small crystallize of yttrium vanadate with neodymium. But also neodymium YAG lasers are used by ASML in their EUV wafer steppers to produce extreme UV radiation at 13.5 nanometers. They They hit the tin droplets with the first pulse of the new react laser, then the second pulse excites the tin atoms to high excited states, and then they go back to the ground state, emitting 13.5 nanometer extreme UV radiation. So the neodymium react lasers are in the wafer steppers of ASML. And even larger scale neodymium glass lasers are used in the nuclear fusion reactor. Hopefully it will at some point produce energy in the future in California. And there's many more applications of lanthanide-doped lasers. Fiber amplifiers, glass fiber optics for data communication. Every 50 kilometers, there's a fiber amplifier using an infrared emission of erbium-3+ to enhance the signals through the fiber optics. So it's crucial for data communication. Solar cells have a pretty good efficiency, 20–25%, but there's a huge loss because of spectral mismatch losses. High energy photons are not used efficiently, infrared photons are not absorbed. And again, lanthanides can be used by using up conversion, down conversion to add up two infrared photons that are not used by the solar cells to convert them to higher energy photons that can be absorbed, or by splitting one photon in the high energies to two photons of lower energy that both can be absorbed, getting current doubling. So lanthanide ions can enhance the efficiency of solar cells by 22%. Money, the banknotes, the euro banknotes, not a big application, but a fun application. They came out in 2002. We measured the spectra in our spectrometers, and we analyzed the spectra, and yeah, we published it 6 weeks later, explaining that the red stars and the red fibers are europium-3+ in the beta diketone. The green fibers are europium-2+ based phosphors. The blue fibers also europium-2+. So it's all europium, and that was confirmed by a contact at the Dutch National Bank. All the luminescence of the europium banknotes comes from europium. So maybe very quickly, I will show some luminescence, and then I'm over. So I think it's also nice to see the luminescence of lanthanides. So this is europium-3+, europium-2+, and green luminescence. And if you combine those three together, then you get beautiful white light. So with that, I'd like to thank you for your attention.
Thank you very much, Andrei, for this very large overview of the optical properties and application of these materials. The question will be connected at the end of the session in the panel discussion. Then it's time now for the second speaker, Mario Ruben from the Karlsruhe Institute of Technology. He will give a speech on one of the most debated topics today in the morning, magnetic properties of free materials and their application.
Yeah, great. Thank you. Thank you. So I just put a short background of my profile just to convince you that I'm not foreigner to the chemistry of rare earth elements, and and in the past, especially for my PhD, I did it under the supervision of Mikhail Bочкарев in Russia in collaboration with Herbert Schumann in the past. Yeah. So my background is about molecular chemistry, homogeneous catalysis, and organometallic chemistry. So we know that rare earth elements are also used in catalytic converters as a heterogeneous catalyst. They're used as MPI reagents, but this is beyond my profile. So I will be concentrated on the homogeneous catalysis, and I will try to present it from the best side. So homogeneous catalysts incorporating rare earth elements. Typically, these are the organometallic discrete molecules which contain the rare earth element in most common 3+ oxidation state, surrounded by the ligands. If you look just in the periodic system. So we have scandium, yttrium, and the lanthanoide series. So the lanthanoide series incorporate the largest by ionic radii elements, and thanks to this large ionic radii, so the properties of the catalyst they are quite specific. The generally rare earth element catalysts, they are much more reactive with respect to different substrates as compared to the other transition metals. And also this is sort of dictated or governed by high electropositivity of the metal center and high oxophilicity. Oxophilicity also makes a problem because this shows the tendency of metals to establish quite stable metal-oxygen bond, so which reflects, let's say, poor thermodynamic stability in the presence of oxygenates, so molecule containing oxygen. So in order to develop rare earth element catalyst, we prefer to use metal in a 3+ oxidation state surrounded by specific ligands. So actually in this chemistry, the nature of the ligand plays the most important role, because the ligand makes the chemistry. It actually decides what type of catalyst will be incorporating given a rare earth metal. It can be polymerization catalyst depending on the nature of the ligand. It can be oligomerization catalyst. It can be hydroelementation, other type of catalyst. So the ligand is an organic molecule in our case. Sometimes this is a molecule which contains heteroelements or even the metals. And by coordination around the rare earth metal center, it creates a catalytic pocket. So this is a part of the coordination sphere of the metal, which is responsible for the interaction with the molecular substrates and the transformation of substrates into the valuable products. So ligands, they provide so-called stereoelectronic effect depending on the nature of the ligand. As I said, we can have different types of catalysis. So this is the scope of the catalytic processes mediated by rare earth elements. Here in the middle, you have a molecular compound. Now we're going to see the molecular compound here, having the so-called spectator ligands and also metal alkyl or hydride function. So this is a function which contains a highly reactive and polarized bond, which will be responsible for a particular transformation. So depending on the reagents, we can have depending also on the ligands, we can have vinylic polymerization, oligomerization, cyclization, hydroelementation, a large series of different chemical reactions, and ring-opening polymerization. So this is the scope of the catalytic processes, and I will give a bit more details on the next slides. Also, organoelement rare element reagents can be used as a stoichiometric reagents. For instance, in the application as the Grignard type reagent for the reduction of different functions. Here you have the examples of Barbier type reactions, Stebbi-like reduction reactions. One of the particular reaction or chemistry developed by Paul Knoschel, so this is the reaction on the bottom. This is a very selective and very efficient methylation of different type of heterocycles with a so-called mixed metal Imamoto type reagent. So this is a chemistry which is related to the construction on functional platforms and for pharmaceutical industry. But again, this is not catalysis, this is stoichiometric chemistry when we need to introduce rare earth reagent in large amount with respect to the substrate. So the vinylic polymerization of alkenes, ethylene, alpha olefins. Here you have the examples of discrete molecular systems which were historically used for the polymerization of ethylene to linear polyethylene. Polymerization with this molecule of large alpha olefins are not efficient because we have some specific deactivation processes. The advantage of organolanthanide compounds that they are isoelectronic to the cationic Ziegler-Natta type catalysts, but organolanthanide and the rare earth element compounds do not require activate, like methylalumoxane. So this is the advantage because methylalumoxane is quite costly and we use it in a large excess. But in terms of the activity, in terms of the stability, they are not, they cannot compete with the Ziegler-Natta system. But we have to remind that thanks to the organolanthanide chemistry, especially the chemistry of lutetium, we were able to establish the mechanism, the coordinative insertion mechanism of polymerization of olefins, which was translated on the chemistry of Ziegler-Natta system and allowed development of more efficient, more selective, more stable modern industrial polymerization catalyst. Another interesting example, so this is a synthesis of syntactic polystyrene. So this is a high value material. This is a thermoplastic material with a very high melting point, but it is pretty much brittle. In the past, it's been used in automobile applications. So let's say making bumpers and different plastic parts of cars. But it is brittle, so it can be modified by the incorporation of ethylene. So our complexes, especially scandium complexes and organolanthanide complexes, they enable very efficient copolymerization of ethylene with styrene, enabling to obtain high impact and the thermoplastic elastomeric copolymer, which now can replace homopolymer of styrene. So I'm giving here the two examples from the Research Institute of Japan. Zhao Minho, he has introduced a binary system based on scandium. Scandium is a very expensive metal. In collaboration with Total Energy, we have developed a catalyst based on neodymium, which operates under mild conditions. Then we can use the same catalytic system in order to copolymerize styrene with the dienes. But polymerization of dienes with a rare earth-based catalyst, it is quite a specific subject because first it is the industrial process. This industrial process, which uses the nickel-based tertiary system. This is a heterogeneous system. And the poly 1,4-cis isoprene. This is a resin material, which is relevant, and this is crucial for the rubber applications for production of tires. So that's why I put a reference to the Michelin company. If you look on the several examples on the bottom, this is a chemistry coming from the group of Ryan Anvander. He used these molecular complexes also for polymerization of butadiene and isoprene to create elastic materials. New type of elastic materials which are introduced by Bridgestone company in Japan for making new type of concretes, elastic concretes for the construction of earthquake resistant buildings. Yeah, so these are the two industrial applications. Besides alkenes, we can use based catalyst for polymerization of polymonomers. But the series of polymonomers is very much limited because of the low functional group tolerance of metal catalyst. So we can produce polyacrylates. In industry, polyacrylates are produced with anionic initiators, but we can use rare earth initiators. We can produce polyvinyl phosphonates. Polyvinyl phosphonates, they are relevant to the proton conducting membranes. We can use for sure other monomers, polymonomers like vinyl pyridine, vinyl oxazoline. Ring opening polymerization. For the ring opening polymerization, we use a cyclic esters. Cyclic esters which are produced from biomass. So this is a chemistry related to the biomass conversion. So two examples I'm giving you here. So this is a polyhydroxyalkanoates. This is a new type of biodegradable polymers. You can find them on the market. For sure, these are quite new materials. They're pretty much expensive with respect to other types of plastics. So they occupy less than 1% of the actual polymer market. So in industry, these polymers, they are produced with the help of tin initiators. This is the case of PLLA, polylactic acid. The PHB, the polymer on the bottom, it is produced by genetically modified bacteria. Yeah. But in our case, we can use initiators. The example we can have here, the molecular complex, in order to efficiently catalyze the ring opening polymerization of cyclic monomers, biosource cyclic monomers, to the corresponding high stereoregular polymers, new type of biodegradable materials. Ring opening copolymerization reaction. This is a modification of the ring opening polymerization reaction when we can use more than one comonomer. In this case, this is a epoxide, and the second monomer, sorry, carbon dioxide. Yeah? So all this chemistry, it is related to the carbon capture. Yeah, because by copolymerizing these two monomers, we can obtain polycarbonates. Polycarbonates, they are also modern materials. These are used in packaging. They are used as medical plastics. They are used as organic glasses. A particular series of the reactions, so this is a hydroelementation. Here we have two substrates. One contains a high reactive unsaturated bond in alkenes, alkynes, imines, ketones, and the second one, this is a reagent which contain hydride ligand, hydride function. So the products of this reaction, depending on the nature of the hydroelementation reagent, can be relevant to pharmaceutical industry if we consider hydrogenation, or especially asymmetric hydrogenation. They can also be related again to pharmaceuticals industry if we consider hydroamination reaction. So this is a very unique reaction which allows to introduce nitrogen in simple molecules. Hydrocellulation, this is a reaction when we introduce silicium. So this is relevant to the organosilicon synthesis and the silicon polymers. Hydrorelation is a quite specific one because the rare earth element catalysts, molecular catalysts, they're capable of quite selective metallation of heterocyclic platforms, which then can in turn be transferred to the corresponding functionalized platforms. So this is a reaction which is also of relevance to pharmaceutical industry. And then we can find tandem processes. If we combine two or more previous catalytic reaction in one multi-step process, for instance, polymerization, hydroelementation. So this is a part of the so-called macromolecular engineering, so the construction of polymers of different topology. Yes, we can do also hydroamination cyclization. Yeah, so this is a construction of nitrogen-containing heterocycles, which are of value for pharmaceutical synthesis. And interesting application of rare earth element triflates. As Lewis acids, they are very stable and remarkably active catalyst to catalyze different processes known from organic chemistry. So I'm just giving here a list because this is chemistry which has been pretty well developed by colleagues from Japan, and just on the bottom I cited them. So finally, if we are speaking about the future of the development of rare earth element catalysts, first we have probably to discuss a few challenges. The main challenge is that the chemistry of rare earth elements is highly sensitive to moisture and water. So that's why all the manipulations, catalysis, synthesis, we have to do under very safe conditions. Argon atmosphere, glove box, Schlank lines. So then quite low functional group tolerance. So oxygen-containing substrates, they can induce different reactivity patterns and just trigger the deactivation reaction. So instead of a catalyst, we just have a stoichiometric reactivity and nothing. So many of these challenges can be tackled by a so-called smart ligand design. Yeah, so we can potentially develop and tune new types of ligands, which can be bulky ligands, which can be chelating ligands, which by steric encumbrance, by stereoelectronic effect, would stabilize and would stabilize active species and would reduce their reactivity with respect to particular oxygen and moisture. But this is a very, very challenging part. And finally, this is a cost. Yeah. So the scandium is the smallest rare earth element, which has the highest trace acidity. It is very interesting and important to investigate in a different catalytic process, but it is very expensive. Yeah. And also lutetium, but then what we also can consider, this is a possible recycling. Yeah. So if we're speaking about the polymerization using rare earth elements like neodymium, yeah, so during the catalysis, the catalyst, the reactive center, they are hidden, they're lost in the complexity of the polymer. So which means that the tires that we buy for our cars, potentially they contain some amount of neodymium. So why not think about recovering it from there? But then it is a very, very challenging process. So I'm done. Thank you very much.
Thank you very much. Also because the last slide is really connected with the morning section. Now it's time for a 10-minute stop. We will be back in 10 minutes, just to give the time also for people from that are connected from the outside. So if you want, in the 6th floor, there is something to drink or something to eat, something sweet. Please. Can I ask you to sit down, please, and start with the session? Maria, Hans-Peter, Nicola? Okay. We are ready for the next speaker. That is Jürgen Gassmann. He will talk about rare earth element for energy transition. And Jürgen Gassmann works at the Technische Universität of Darmstadt. And in 2013, he joined the Fraunhofer Institute for Recycling. Is correct because it's written in German. For recycling and sustainability.
Right, materials
like
recycling and resource strategies. It's
okay. Okay, and he works on a rare earth permanent magnet, especially neodymium, iron, and boron. He has been the head of the department magnetic materials, and during his work at the Fraunhofer, he has been responsible for the installation of a pilot plant for production and recycling of rare earth permanent magnet. Please.
Thank you for this kind introduction. I was asked to talk about rare earth elements in the energy transition, and this is how I also structured my talk. How I build it up, it might fit better to our morning session today, but nevertheless, we can discuss afterwards. So I think you hear a lot of rare earths on the whole day. Here comes the last version for today, actually. I can't go to the next slide. I'm clicking. Yes, now it's working. So basically, the whole idea is we need to reduce carbon dioxide emission. And here you see a chart from the Climate Action Tracker for the European Union, but you can also find it on their homepage for all the countries which are tracked. And we see in the European Union, our effort is insufficient to meet Paris Declaration. So what we do is not enough to meet our goals by the year 2030 and 2100, for instance. In different directions, one can see that based on a fair share trade, but also on domestic pathways, we need to be better. And for that, we need new materials. And these materials, which can be, for instance, magnets, might be defined as critical. And the chart on the right-hand side, we already saw today, light and especially heavy rare earths are defined most critical in terms of supply for the European Union. And criticality can be on different scales. So it can be like geopolitically criticality, like it's now, it's a moment. It can be geological criticality, which we don't have with the system. It can only be price. But it can also be like environmental impact during mining, etc., why a material is called critical. And we as Europeans, we don't have enough resources for our own demands. Therefore, we might need to think about where to get these resources. For instance, for batteries, lithium and cobalt, but also platinum group metals, but also especially rare earths, which is a topic for today. So if you see how much magnets are used in EU, you will recognize that the demand will increase in near future very much, driven by electromobility and wind energy. So in a wind turbine, you have about 5 to 10 tons of materials. Most likely the offshore wind turbines, which are using this high amount of magnets. In medicine application, the amount is lower, but still you have a ton. And for automotive applications per electromotor, you have about 1 to 3 kilogram per device. And obviously, in our electronic equipment, we have only smaller amounts in the gram scale. However, there are billions of devices, so it's like a factor of scale here. So, question is, how sustainable are the materials which we need for this energy transition, and how can their demand be secured? So basically, it was also mentioned this morning that primary mining in Europe and also partner countries might be one reason, or might be one solution, and it will be one solution. However, also using material from our technosphere by recycling can help to sustain some of our products, and also substitution. I do also think that if it's possible to substitute some of the material, we can lower the general demand of the rare earths, which we will need. So the talk today will only highlight the recycling part, actually. So like it was mentioned, so what we did, we set up a facility for R&D purposes. So I'm from Fraunhofer. Fraunhofer is the biggest organization for applied research in Germany. We have about 76 individual institutes. My institute is located in Hanau, and we are dealing with critical materials, not only rare earths, but also rare earths. And here we set up a facility, is more or less a zipped magnet factory, where you can produce in the scale from 10 to 50 kilogram permanent magnets. So we are doing research in substituting the rare earths, but also on recycling them. And what you also did set up is like the analytics which you need to understand the material. And if you think about magnet recycling or recycling in general, one always has to think about different things. So basically, what do I want to sell at the very end, and what do I want to reach? So like it was mentioned this morning, there are several routes to go in terms of magnet recycling. A long loop elemental recycling approach, where you go back to the separated elements, or a short loop functional recycling approach, where you stay within the system of neodymium iron boron. However, what you will end up at the very end is totally different. For instance, do you want to have the material with the highest physical performance, so the highest magnetic field from a product? Then you need to go the elemental route. Or do I want to have a material for the lowest cost? You might have a different recycling route. Or do I want to have a material with highest sustainability? So these questions need to be phrased and needs to be answered before a recycling process is implemented. So for instance, for the long loop recycling processes, there are different processes also mentioned already: hydrometallurgical processes, pyrometallurgical processes, also electrochemical processes. The good thing is almost every type of material can be processed with this different kind of technologies. So also contaminated scrap, for instance, can be processed. Also small magnets can be processed. However, the material to go back to the oxides and to the separated oxides, quite a few process steps are needed. Energy is needed, and also chemicals are needed. And then we have the separated oxides. And like it was mentioned by Milan Groholz this morning, the metallization is lacking in the European Union. There's like one company in UK with 50 to 100 employees who can do metallization of rare earth oxides nowadays, but there is none in the European Union. So if you can produce these oxides, it doesn't mean that you can produce magnets, because the intermediate step in producing metals is lacking. And like we learned this morning, it's the most energy intense step. So most likely the less lucrative step to be performed. Nevertheless, there is a reason also to go in this direction, since these oxides, which are produced from scrap magnets, are basically the same oxides than oxides produced from primary mining. So with this, you can produce all types of magnet materials which you need. When you now think about short loop recycling, the difference is that this process is depending on the scrap material. So if your scrap is oxidized, it's a problem to the process. The magnetic properties of your recycled product will most likely be dependent on the magnetic properties of your scrap material. If you have a mixed scrap, it might be harder to implement. Nevertheless, there are just little number numbers of process steps needed to do that. And therefore also sustainability is potentially highest because one can produce magnets with very good properties, and the processes one needs for that are basically the same or similar ones than one already uses in primary magnet production. So one can go for hydrogen decubitation or HDDR or melting procedure. You see here on the top how hydrogen is incorporated into the magnet due to tensions and stress. Due to the hydrogen incorporation, you powderize basically your system, and this powder can then be remilled, reused, and the sintered magnet can be produced out of this powder. Another way to go is melting the material. During melting, also some of the oxide is then removed. This material can be transferred into hot deformed magnets, into polymer bonded magnets, onto sintered magnets. However, the melting step also here consumes energy, which can be skipped when one starts directly with a hydrogen decubitation. Nevertheless, what I want to show is there are different ways to go. I don't want to say that some of them are bad or some of them are good, because they are all heading in different directions in terms of feedstock, which the people get, in terms of products, which they can bring to the market. With the long loop recycling, basically, like I mentioned, the highest magnetic properties, that's a huge advantage, and that oxidized materials can be used. However, one has, on the disadvantage side, high energy consumption and the metallization, which is needed. Whereas for the short loop, in principle, the magnet with a high sustainability can be produced. However, it's not suitable for all the scrap materials. Therefore, I think on industry sides, there will be different technologies on the market by the year 2030, where the Critical Raw Materials Act will come into work. What we did in a research project is basically we didn't want to show like recycled magnets. What we want to show are recycled products. So most people know what a magnet is, but they didn't know how it measured the performance of a magnet. However, most people know what a motor is and what the performance of a motor is. So the magnet is never used as itself. It's always put into a system, and the system is then used. So we took different kind of systems like e-bikes, like the scooters, which you find everywhere on the street, basically. And also the lifetime of the scooter is quite low. So hopefully you find them in the recycling places and not somebody buried in the river or something like that. So we took these devices, dismantled them, measured the magnetic properties, and tried to produce these types of magnetic properties with recycled products. And we did measure basically not the performance. So we also measured the performance of the magnet, but basically we measured the performance of the motor. So on the very left-hand side, you see that we not recycle a product, but we reused a product. So we took magnets from an MRI device, we just cutted them, recoated them, magnetized it again, and used it in a motor, because magnets usually didn't get destroyed. They can be demagnetized, but they can also be magnetized again, and they can be reused. For an industrial purpose, the reuse is just a showcase. I don't think that it will really have a place somewhere, but recycling, also short loop recycling, can be also in this industry available in near future, because one can produce all kinds of physical properties and all kinds of geometries with that. And the two right-hand side motors, you can see, basically, if the lines fit, you will see the very same energy which you get out of the motor from a primary magnet and also from the recycled magnet. On the very right-hand side here, the recycled magnet was performing a bit better, but it is the comparison a bit false because we used other materials. Nevertheless, the material which we use could be used in this device on a primary scale. and it would also work. So what we want to show here is, in principle, the technology is there, and it can be used, which is actually quite good. However, situation is a bit more complicated. It was discussed that also this morning that electromobility is a huge driver, and also wind. We are expecting the first magnets back from wind in the mid-30s by beginning of 40s. So still 10 to 15 years to go until the very first magnets in Europe come back from wind. So there are still something which is refurbished, but when you really think about end of life wind turbines, you start at 35, something like that. From motors, it will come earlier. However, here you have less magnet material, still enough to be recycled. However, the devices are so different. And for a recycling, you really need to get access to the magnets. And these magnets are not only in the car, they're also in the motor, which are in the most cases like glued in a device. And you don't have really good access to this material. So this product needs to be designed not only for a use phase like they are now, they also need to be designed for an end of life phase to be better recycled. So labeling is great. However, if you know that the magnet you need is in the product and you can't afford the costs you will need to get the magnet out, then we are in a dead end again. So all the motors which are on the market today, and about 90% of them are using permanent magnets in electric vehicles. The design is different, and most of them aren't really optimized for an end of life, for a dismantling, for a design for recycling. So this is something one has to work on. However, there are some companies already now in European Union starting the recycling in Germany, in France, but also in UK and in other countries. There is movement on the market, and I show you here for a circular economy, you basically need the full circle. So you need the collection, you need to dismantle your devices, you need to process the new magnets, and then you can bring it into energy transition devices like wind energy or like electromobility, which we need. However, if something of the circle is missing, like the metallization, it might be a problem. And here, I think, and that was also my question this morning, is like achieving an added value by using material which is here. This must be also shown and appreciated by companies and by society. So if we want to be independent right now, most likely we need to pay a premium for our product. And at least partners which we are talking to, they see there a problem. Because rare earth prices didn't skyrocket in the last 2 weeks or 2 months. They stay quite stable. People are waiting to get their material. They might get them. Also after 2011, after the rare earth crisis, the industry went crazy. After 3 months, everything was normal again. So I'm really curious how this will turn out. But at least now, I think that at least companies where I showed that we really have a huge demand in Europe, they don't see that this added value is there, that material can be used from our technosphere. And this is quite a problem where I also think that policy need to step in to assist that this material really is on the market by the year 2030, because it's great that we have this goal that 25% should be recycled by the year 2030. There should also a company be capable to do that by this year. And this might be a challenge. So with this, I'd like to summarize my talk. So I think that technology for recycling, for materials, for electromobility, which we really have in Europe, a lot of companies building cars, and we have also companies for wind, to have the wind transition, energy transition, it's all there. They also need to use a material which will be in Europe, also for the price which can be competitive in Europe. So there will be several recycling technologies, for instance, so that we can use at least some of the material. There are different studies. So about 10 to 20% of our demand can really be come by recycling by the year 2030. So we might miss the 25% a bit. But nevertheless, at the moment, recycling is almost zero. The magnets which are produced also from short loop recycling basically can also already be used in nowadays products. However, the products also need to be designed more for recycling. So with this, I'd like to thank you for the attention.
Thank you very much. And with this speaker, the section ends. Now it's open for question, both on the scientific part, that is a huge part of this afternoon, but also with what we heard in the morning and with all the problem related with the strategy of the EU compared with all the problem of the market and compared with the other part of the world in which technologically speaking, these problems are already partially been solved. So please, Peter, can you come to guide this panel with me? There is any specific question that you would like to raise for each speaker? Yeah, yeah.
Many questions, but I will start with the first one, actually for Professor Kirillov on the catalysts, because in your conclusion, you mentioned the problem of stability of earth-based catalysts, but they're widely used in the industry. So like, is this also a problem at the industrial scale that they're being used under like inert atmosphere and so on?
Yeah, okay. Thanks, Marie, for this question. Well, my answer could be very short. I would say that if there were no other process, well, sorry. Yeah. If there is a process for polymerization or whatever catalytic transformation without rare earth elements, with a simple transition metal chemistry or main block chemistry, that one should be used. Because again, rare earth elements, they're costly. Yeah, you need quite specific equipment, quite specific atmosphere, quite specific skills in the manipulation with that. And if you can replace rare earth with any type of other metal, that would be actually a big profit, a big gain. I just can give you example from the past. Yeah, for instance, I had a discussion in the past with Herbert Schumann. So he developed a series of catalysts for the polymerization of acrylates to produce quite nice polyacrylate polymers. So he gave this catalyst to the industry, and they simply oxidize them, decompose, because they're not equipped, they do not know how to manipulate them.
Not an academic analysis, but I think some of the catalysts that I used have because they're really rare, like platinum catalysts. The abundance is so low that from to and there, the recycling rate is quite high because of the low abundance. I think the 3D is clear, but I think if there's a place to replace 40 or 5D transition matter catalyst by rare earth, there may be less risk, less cost. Those are the rare earth.
Yeah, maybe I prepared my answer in a quite not clear manner. Yeah, it's a very good point because for the late transition metal catalysis, palladium catalysis, platinum catalysis, if you know how do they proceed in industry, they use, for instance, a palladium acetate as a catalyst. I put it. They use 20% of this material. They do not use any ligands. Yeah, so you have a reaction. You obtain a product. But because of the absence of the stabilizing ligand, palladium or platinum, it is reduced to the metallic state. But they have the technology to recover it, to reconvert it to palladium acetate. Unfortunately, no similar technologies can exist for the rare earth elements for the moment.
Maybe I can add something by myself because I'm also working catalysis. You're talking about the air sensitivity, and this is usually a matter of competition. So if you look in Ziga and Etta catalysis, where you work with high reactive aluminum compound, yeah, the companies transport it in a train, something I dare not to open in the lab. Yeah, so they can handle it. Of course, higher security standards means higher costs. So it's always a matter of competition. If you have a better, more stable process, of course they do. If your process is superior, that materials are sensitive, and they can make money out of it, they will do it. So that's what we experienced in the past, and I guess that we will see in the future.
I have a question regarding lighting. When I take in my hands LED lighting appliance, first it's not even clear to me if I can replace the light in case I have to replace it, because we were used to change lamps. It was very easy. You went to the shop, you buy and you replace. In the case of LED, it's not even clear this part of the story if you have to throw away the whole appliance. This is my first problem. The second, which is related to the today discussion, what about recycling of that small yellow spots in the light? Does it make sense? Is there any interest? Because we have heard about a lot of recycling, but it's all about typically a very big device, which makes sense. But what about lighting, which are very small spot of things?
Yeah, both are very good questions. To start with the first one, the lifetime of white light LED is extremely long. At least 30,000 hours. If we look at the old incandescent lamp, the lifetime is about 1,000 hours. So you have to replace the light bulb every 2 years, maybe. A fluorescent tube lasts about 10,000 hours. An LED, at least 30,000 hours. Unless you buy a cheap one from China, then the electronics may die. But if you have good electronics, they last 30,000 hours or more. So in your lifetime, you probably never need to replace it. So replacement is not a problem. Then recycling, yeah. There's about 1 milligram of phosphor in an LED. In a fluorescent tube, there's about 1 gram. The amount of light that comes out of fluorescent tubes is about 10 times higher. So you need 10 LEDs to have the same amount of lumens, the amount of light that the eye perceives as for one fluorescent tube. But it still means that you have 100 times less material. So it does not make sense to recycle that. And also it means that the pie chart that we saw of about 5% that goes to phosphors in 2016, that will really decrease. Because we need, yeah, the LED phosphors are 100 times producing 100 times more photons than the old fluorescent tube phosphors. So the amount of materials in there, yeah, is so small, doesn't make sense to recycle it. Also because it's embedded in some polyacrylate. So yeah, recycling is not an issue there. It's not needed because the amount is very small, and economically that will never be feasible.
Please, Peter.
Yeah, I have a question myself, and this goes to the last lecture. It's maybe a very naive question, but in my naive thinking, if you cannot remove a magnet out of a multi composite material, so I thought if you simply crash the whole material, it's nothing easier than get a magnet out. That's in my naive thinking. So maybe you can give me some idea why I'm wrong.
So basically, working.
He's gone.
So the good and the bad thing about magnets is that they are magnetic. And when you, for instance, take a motor and go to a shredder to what it's actually happened today, because basically the people are recycling the copper out of it, and then they get the soft magnetic and stuff like that. So the motors are shredded. The magnets are very brittle. They are fragmented and they stick to your shredder everywhere. And basically it will just pollute your shredding device and you will basically lose it because you can scrap it off with whatever kind of material. So what you really need is you need to separate it. There is also work, for instance, in Japan that they like melt everything and then get the rare earth out from the liquid, which you can do, but you have the melting step. You can demagnetize it in the first place where you need heat. But like I said, if you really smash it down, the magnets will get destroyed and it will be hard to collect them. So usually what happens is that this permanent magnets, they go into the iron, are recycled with iron, are formed as slag, yeah, and then they are lost. For an efficient recycling, some form of separation might be needed, and for that, demagnetization might be needed in one way or the other, and this can be done on different ways. Heat, hydrogen, or electromagnetic fields are to use there. But to really work with magnetized material, for instance, from wind, where you have kilos of magnetized material, which you can't use with conventional tooling, is quite dangerous and special. It can be done and needs also be done, but it's also complicated.
Good, thanks.
Okay. Any other question? Yes, please.
Yeah, maybe if to also last speak, also relate to what Peter asked. What is the demagnetization time of the neodymium iron boride magnets? Because note that the ground state of a magnet is, of course, non-magnetic. It's all the domains, if all the magnetization can stay inside, that's the ground state. Because you've magnetized it, so all the domains are aligned in the same direction. Does it slowly revert back to the ground state over time, over 1 year, 10 years, 30 years?
No, in principle, it never goes back, except if you reach a temperature which is too high. And then it can be very fast, within milliseconds. So yeah, for neodymium iron boron, it's about 400, 420 degrees C, depending on the composition. So the performance of this material is also decreasing with temperature. Therefore, you need to cool your motor, most likely. And basically, that's the only way a magnet can get worse. If it can also corrode if you get some oxygen inside. But if you protect it, and if the protection is good, magnet will be as good at the very end. However, it can be demagnetized by temperature. Yes, but that's not that much of a problem. You can also have, for instance, if you have like this synchrotron radiation, where you also have magnets, this can also have an effect on your magnetic field. So there are different things which can have an impact on the magnetism, but most likely in operation, it's temperature.
And then the second question, you already partly answered it. What is the demagnetization temperature in the processing of the magnets at the end of life? Do you then heat them up to about 400 degrees to demagnetize it?
That was the most easy thing, to heat it about the Curie temperature, and then you can handle it like a normal material. That's basically done. And we also showed when you have like a motor and you heat it up and you had adhesives which are still working at these temperatures, you might also end up with a problem because then the magnet isn't magnetized anymore, but it's still sticking within your motor. So also here, there might be one or another material which might be better for operation, but not so good for recycling, and better for recycling and not so good for operation, most likely. Yeah.
Thank you.
Please.
I have another question regarding wind aerogenerators. What is the driving force of the driving the end of life of this machine? Is it the wear and tear of the blades, the magnets, something else? Because when I see them, it seems that they are eternal, but they are not clearly. So what is the part which is more prone to getting old and needs replacement?
So I'm not from the wind business, but I think it's not the magnet. I'm quite sure about that. It's the moving parts. So you have a generator inside where you have some gearings, some stuff and bearings and stuff like that. So I think this will most likely be the things which yeah have the biggest effect on lifetime. Another thing might be regulation. So for instance, if you build up a wind generator on a place where it's legal to build it, and in 20 years of time, you basically can build there a wind turbine with, I don't know, 10 times of megawatt. So you are just replacing it because the device which you can install now is way better than the ones you did 20 years ago. And I don't know the whole regulation, but at least in Germany, it's quite complicated to set up some wind turbines, and you can't do it like everywhere. So you need to have some distance to housings and stuff like that. So I think this is the answer. So replacing it by a better device and the moving parts, which will begin in.
Okay, thank you very much. This, by the way, makes photovoltaics fantastic because there are no moving parts, and that's last for 30 years without any problems.
Okay, I have a question. Because today in the morning, we heard about standardization, monitoring, and mitigation that are driven by China, Germany, and France above all. I'm asking all the researchers in the different countries how they deal with regulation and with boundaries that each country, and how this influences the relationship with industry. No answer.
I'm a fundamental researcher. I like to understand how the light emission goes. So I don't worry about the regulations. That's the next step. So also when people say you use this toxic element that will never work for present regulations, I don't care, because if you can do good science, understand the physics, how it works, I'm doing the research and understanding. Maybe a nice example is that I also go to a big phosphor conference. It's the Phosphor and Quantum Dot Industry Forum, where industry and academic research come together. Really good, we can inspire each other. GE presented talks that they had a very nice narrow band green emitting phosphor, compound X. They did not say what it was. But yeah, I saw the excitation spectrum through a lot of lessons lifetime. And this green material could also sensitize European 3+, which is the perfect red emitter. So they would have a perfect narrowband green and narrowband red emitter. But from the lifetime of the emission spectrum, I could see this is uranium. Now, I understand why they called it compound X. And I asked the question at the conference, that is this uranium? And he said, I am not allowed to disclose what it is. Makes sense. So I think it's uranium. And later I've talked to people, and yes, it is uranium. And in the amount they use, this 1 milligram, you can do it safely. But to get it through regulations accepted by the public, I think that will never work. So it will never be commercialized. But yeah, as a researcher, I don't worry about it. I do research. That's the problem of the industry. Yeah. I do my research, and then if I find something really good, industry can try to implement it. And if they fail, well, their problem, not my problem. I've got my understanding. I'm at the university. I'm there to do good research, to experience or find out how nature works.
I don't remember.
No, I think I follow on what you just said. I think you cannot really have innovation if you're focusing on regulations that already exist. So it can be a limiting factor, and you need innovate. Exactly. Yeah.
So Hans Peter?
Oh, I just wanted to add to the, how to say, issue of regulation, and there's also public opinion. And, the regulators are chased by public opinion.
Yeah.
Now, some of the, how to say, rare earth metals have in public have a bad reputation. And my question is, which elements are most exposed? They're uranium, you mentioned uranium.
Well, that's an actinide, of course.
Oh, that's an actinide. It's not a lanthanide. Okay.
The lanthanides are not that.
So they're harmless at that scale.
The gadolinium for MRI imaging has caused some health problems. When you inject the gadolinium as photostatic for MRI, that has been shown with some health problems. So injecting it in the bloodstream may not be one.
So gaining public trust for lanthanides is still a bit of an issue. Not for basic researchers like you, but maybe for the Fraunhofer. Yeah, I know.
I think the bigger problem is really during mining. It was shown this morning how this material is mined. I think that's really an issue. There you have exposure to uranium and thorium. These are the two elements always come with rare earth oxides, and you produce a lot of waste. So the numbers were shown how much wastewater you are producing, how much I don't know, dust is produced during the whole mining. I think when you have the rare earths as elements, most of them are not that much critical because they don't really come into our contact, except when you really need to use MRI, where you then maybe also has other issues in terms of other radiation which you might have. But I think that's not the issue. But if you really work into primary processing, and some might do in Europe because we might want to mine ourselves, I think the primary mining is the bigger issue.
Next to the Bayern-Ober mine, there's a 7-kilometer wide lake, very acid radioactive wastewater. And it's just sitting there.
Okay. Any other question? If there are no other questions, we'll give the word to Peter. Sugar.
The chemistry. Can I keep my presentation on again?
Yes.
The chemistry is very appropriate for the EuChemS, especially here in the Europe.
The connection between people and researcher is very much appropriate for EuChemS.
I really wanted to share this so close to the European Parliament because this chemistry about Europe. chemistry budget. Is the European Union or more or even it's gone, but there's hidden information about Europe in the periodic table. And it has big concerns with small countries like the Netherlands. We are worried that Germany and France determine what's happening here. There's no article in the news that precies zoals nooit Europa House, is that the face of the new Europe. And then around and very recent picture. Met Macron.
We will see.
Yeah. Well, Germany and France decide something. It doesn't matter if the Netherlands or Spain or any of these things. That is what happens. Now that information that France plus Germany is Europe is in the periodic table. If you look at the periodic table, it's the element number 31, gallium, France. Right next to element number 32, that's the neighbor, germanium. Now if you nuclear fuse element number 31, gallium, element number 32, germanium, you get element number 63. Now what is element number 63? Europium. Now that is coincidence, but I think it's very nice on the table from our devices. I think that's a wonderful coincidence. Periodic table has this information about that.
We'll take it in the
Yeah.
Thank you. And please, Peter, for the conclusion.
Yeah, okay. Thanks a lot for that really nice final words, which I do not comment as German. Okay. Yeah, thanks for everybody for coming. Thanks for the organizer for hosting us. And I guess we did. Okay. Yes, thanks for hosting us. I guess we had a really nice scientific day. So at least I enjoyed it. I learned a lot. Also, I'm working in rare earths for quite a long time. It's really nice to see the field from different viewpoints and applications. And I hope that we could also transfer all the knowledge to the lawmakers and to the public. And with that, I thank everybody. I wish you a good trip home and see you sooner or later at some conference. Thank you.
Thank you again. Has been very nice today in the morning and in the afternoon. I always thought that a fragmented European community doesn't serve too much, but a community of researchers that work together is very useful for autonomy of Europe and the progress of science. So we will keep you informed. There will be a follow-up of this meeting so we can help researchers to have EuChemS as a reference place for their sharing information and if we can help somehow to improve from any point of view your research and your approach toward Europe, we are here. Thank you very much. Thank you, Ninetta, and thank you, Claudia, and thank you, Chiara, for your help in organizing this meeting. Welcome back to your place. I have to run also to get the train to my place and keep in touch. Thank you very much.